in a previous section, we saw that an amide, which is, just to kind of refresh your memory on that functional group, is on a lower rung in the stability ladder relative to a carboxylic acid, which means that the conversion of an amide to a carboxylic acid is energetically unfavorable. However, the transformation in this equation is known as an amide hydrolysis. It can be carried out by treating an amide with OH-, a base, followed by an acid workup to convert it to a carboxylic acid. So let's look at the mechanism for this reaction. So we're going to start out by writing our reactants. Let me back up there. I think I'm going to write it like that. Okay. And the first step is going to be a nucleophilic addition reaction, where these electrons are going to come in and attack that guy there, and those electrons are going to pop up there. Then we have a tetrahedral intermediate, and it will undergo a tetrahedral collapse. For a nucleophile elimination. Now, the reaction's unfavorable to this point. And then what happens is we end up with an irreversible proton transfer that helps favor the products. And what happens here is this base that we've already made and is floating around, let me try to make that ring a little better. Okay. That base that we've made that's already floating around is going to come here and steal that proton. And when it steals that proton, those electrons are going to go back on the oxygen. And so we have a proton transfer. When that occurs, we've got this complex here. And now we have an acid workup. And in this acid workup, we add that H+, and we have a proton transfer where these electrons are going to grab a proton, but also these electrons here are going to grab a proton. So you add an acid and everything gets protonated, okay? And now we have our carboxylic acid right here. So I just want to go over things a few other times. The direct formation of the carboxylic acid from the amide is energetically unfavorable. And the reason it's energetically unfavorable is because of the negative charge on the nitrogen in the leaving group is poorly stabilized. So, the direct formation of the carboxylic acid from the amide is energetically unfavorable because the negative charge on the nitrogen in the leaving group is poorly stabilized, right? So this reaction is reversible all the way through the second step. Okay, so if this is the first step and this is the second step, we're irreversible to this point. Okay, now the proton transfer step here, though, is we are reversible. We are reversible to this point. The proton transfer step here is irreversible. Okay? And so this is really similar if you're like, ooh, I feel like this is similar. It's similar to saponification mechanism. So without the proton transfer step right there, without that wet acid workup, no appreciable amount of the product would form. Because it's irreversible, it drives this reaction towards products, right? So just like with this saponification reaction, we are going to look at the free energy diagram of this to explain why the amide hydrolysis takes place. Notice that the immediate products from the nucleophilic addition and elimination are higher in energy, right, than the overall reactants. The carboxylic acid, right, remember, is one rung higher in the stability ladder than amides. So that direct acyl substitution to form the carboxylic acid is going to be generally unfavorable. The irreversible proton transfer, though, is this third step here, right? And it lowers the energy dramatically, right? Here to here. So really, really lowers it. And I want you to note that the product from the deprotonation, that carboxylate anion, right, is one ring lower than the initial amide on the stability ladder. Notice that this carboxylate anion is stabilized by resonance delocalization, right? And so just something to help explain the energy levels and why we see this reaction go. Now, although the carboxylic acid is often the desired product when an amide is treated with a hydroxide, sometimes the goal is to isolate the nitrogen-containing leaving group. And this is the case for the Gabriel synthesis. So the Gabriel synthesis uses phthalimide, right, which is shown right here. And it's treated with a strong base. So like this is showing potassium hydroxide, followed by an alkyl halide. Then you can see where that alkyl halide attaches here to this nitrogen. So there's two carbons there and they attach right here. Subsequent hydrolysis then frees this to be a primary amine. So it turns this alkyl halide into a primary amine, and you use this reagent every time to do it. Okay, so if we want to think of it that way. So let's look at the mechanism of this. So we're drawing the phthalimide. And we're going to have a proton transfer as our first step. what we see happening here are these electrons are going to come in and grab that, and those electrons are going to go on the nitrogen. Then okay, we have the bromine that comes in, and I forgot a charge. Don't be me. Don't forget the charge. It's got a negative formal charge on that nitrogen. These electrons are going to come in and they're going to attack that. And those electrons are going to go on the bromine. So they're attacking that carbon because, remember, it's partially positive, and the bromine is electron withdrawing. Okay, just like we've seen before with the alkyl halides that we've looked at. I'm just looking back and forth, making sure I'm drawing this right from the previous. I'm going to count my carbons, so I know I should add 2 carbons because the alkyl halide has 2 carbons. Okay, now this nitrogen here, that's the leaving group. And so what's going to happen, sorry if there was a stutter there, I had to, if it broke up a little bit, I had to stop the screencast for a moment. All right, so now what we're going to do is we are going to add the OH minus. And when we look at this, this is going to be exactly what we saw in the previous mechanism to convert an amide to a carboxylic acid. So steps 3 through 5 here are kind of those 3 steps that we get from equation 2212. Okay, so I want you to go and I want you to look and find those steps 3 through 5 from equation 2212, and I want you to write them in. So I want you to practice, right, applying that mechanism to this mechanism here. Okay, so I want you to take what you learned before and apply it here because they're the exact same steps. Okay, so the steps 3 through 5 here are this. There's 3 in that equation 2212. Now, once you do that, you should get this product here. Okay, then we're going to add an OH again, right? And it plays again in those same, like, kind of the same thing happens where the steps 6 through 8 here are the same thing as equation 2212 again, right? Where this nitrogen here is the leaving group, okay? And this one here is the leaving group. So I, again, want you to practice applying what you learned in that mechanism to this mechanism, to a new situation. On the test, you would have to write out all of these steps, okay? So I want you to practice it and then come and get it checked. And then our final product here is this, but that's not really the product we're interested in, right? It's the primary amine here. So I just want to summarize. Steps 3 through 8 are 2 successive acyl substitutions, similar to that first 3 steps of the amide hydrolysis. And so work through that. We're just, again, like I said, we're just taking something we've learned and we're applying it to a new problem. And then come and get that checked. But if this was asked on a test, you'd be asked to show all of these steps. You can't just write steps 3 through 5 and then steps 6 through 8 are the same as equation 2212. Okay. Now, in all the acyl substitution reactions we've talked about so far, one reactant is an acid derivative where the carbonyl carbon is bonded to the leaving group. However, when we look at haliform reactions, like we see here in equation 2215, a methyl ketone, which is, when we talk about a methyl ketone, sometimes that has the general form RCOCH3, right, which is shown right there, also can undergo acyl substitution when it's treated with excess bromine in aqueous sodium hydroxide followed by an acid workup. One of the products, the bromoform, which is the HCBr3, is an example of a haliform. Okay, and a haliform has the general formula XCX3. Sorry, that's HCX3. Where X is a halogen. Okay, now a reaction that produces a haliform is known as a haliform reaction, and haliform reactions can also take place when a methyl ketone is treated with chlorine or iodine, and if that happens, it produces chloroform, which is HCCl3, or iodoform, HCI3. So they don't really use fluorine quite so much. Fluorine tends to explode, so people don't, it's just not practical to work with it. So notice in this acyl substitution that the OH appears to replace an H3C minus, which is a very poor leaving group. So I want us to look at the mechanism and see kind of why that is. So when we look at this mechanism, I'm not going to have you draw this out. Well, let me back up. I'm not having you draw this out in your notes, but you are responsible for drawing the mechanism on a test if I ask. But I do also want you to get some experience reading mechanisms, because when we look at the mechanism here, this would be like a mechanism we would see in a paper. And so I want you to have some experience in how you would look and you would read this. Now, in steps 1 through 6 of this mechanism, the 3 alpha hydrogens on the methyl group are replaced by bromine atoms by the alpha halogenation mechanism that we talked about in section 10.6. And so you should be able to do this. So go back to your notes from section 10.6 and work through the first 6 steps, okay? And then have that checked. Now, what will happen is we'll get the resulting tribromomethyl ketone, and it will undergo an attack by the hydroxide through a nucleophilic addition. And so when you look at this, you're gonna start here and you're gonna think in your mind, all right, these electrons come here, they attack this carbonyl carbon because that is partially positive, right? And then these electrons are gonna be bumped up here, okay? And we have that nucleophilic addition reaction. Then what's gonna happen is we end up with a tetrahedral intermediate, and there's a tetrahedral collapse where these electrons come down here and then bromine is eliminated. And so we undergo that nucleophile elimination. we have a proton transfer where these electrons come out and they grab that proton and pull it back, and then these electrons go onto the oxygen. That's the irreversible step. So notice a lot of these proton transfer steps that we're looking at are irreversible. Then these electrons, through the acid workup, come out and grab a proton from the acid, and now we have a carboxylic acid. So note that Br3C- is really the leaving group, not H3C-. So what this mechanism does is it takes a really poor leaving group, which is CH3-, and the first 6 steps turn it into a better leaving group. And because what happens is those bromines that are on the carbon withdraw electron density from the carbon, stabilizing it. So that Br3C- is a more stable leaving group. Now, why are all 3 of the halogen atoms necessary? Okay, so why do we need 3 hydrogens here for this to work? Well, it's necessary to make the carbanion a suitable leaving group. So one of the things that we know is that an ethyl ketone does not undergo acyl substitution because it only gains 2 alpha hydrogens. And so that's not enough to stabilize that carbanion, right? So we absolutely need that 3rd halogen. Now, prior to the advent of spectroscopy, the iodoform reaction was commonly used to test for methyl ketones, right? And so what would happen is iodoform is a bright yellow solid at room temperature, and it's insoluble in water. So if you had a bright yellow precipitate that appeared on treating an organic compound with I2 in basic solution, it was likely that it was a methyl ketone. So this would be a positive iodoform test, which was, I thought, kind of an interesting piece of history. So in the next section, we are going to focus on some hydride reducing agents.